So I'm a faculty in electrical engineering and computer science at MIT. And I've worked quite a bit on learning graphical models, so probabilistic graphical models, trying to figure out interactions between different kinds of variables that you can observe. And in particular, I'm interested in doing this in biology. It's usually causal relationships that you want to learn. So these interactions are causal. And so you want to, for example, know how different genes interact with each other, what is upstream, what is downstream. And so that's what I'm going to talk about in the 3 lectures here. And you'll see that, whenever you think about these graphical models, these networks in statistics, that actually leads to quite a bit of geometric structure, algebraic structure, and combinatorial structure in particular. And that's all what we want to discuss in these 3 lectures. But today, what I'm going to do is really just give a very, an introduction into graphical models, so that I can then get started tomorrow and then the day afterwards, to really go a little bit deeper into the actual algebraic, combinatorial, and geometric structure that is there. Okay, so with that, let me actually get started. And as we just discussed, please do just interrupt me. I mean, if you feel more comfortable writing something in the chat, that's fine as well. I'll hopefully see it, but otherwise, please do interrupt me and just ask questions throughout the hour. Okay, so introduction to graphical models. So what are these graphical models? So these graphical models, as somehow the name says, it has to do with a graph. So it is a distribution over a particular graph, or a distribution that can be described by a graph. So these graphical models are probabilistic models, where this graph actually describes the statistical dependencies that are there between the different variables of interest. And the distribution and these dependencies are described by a network. And so these models are used throughout many different applied areas, throughout the natural sciences, social sciences, economics, etc., to model interactions. And these graphs or networks, they can, and I'm going to use these names or words interchangeably, they can be directed or undirected. They can they can have latent variables in them. They can be fully observed. So this really depends on the particular application that you're working on. So for example, if I'm thinking about, I see something popping up, but I think this is all good. So for example, if I'm thinking about biological applications, as I just mentioned, like for example, gene regulation, well, there you really care about the directions, right? Because, I want to know which gene is upstream. In particular, if I intervene on the system, say I knock out a particular gene, I set its expression to 0, well, I want to know what happens downstream, right? What are the genes that are actually changing? Or say you have a drug, and a drug is going to perturb a particular protein. Well, you want to be able to know what is actually going to change when you apply this drug, right? So there it matters on the directions, because only something that is downstream is actually going to change. Nothing upstream is going to change. However, in other applications, like for example, what I have over here, like weather forecasting, well, although some people can now intervene on the weather, but usually we don't want to intervene on the weather, right? We don't want to be able to understand what happens when you change something in the system over here, over there. Well, I mean, there are also such questions, but in general, for the standard weather forecasting that you want to do every day, that's not the kind of question that you want to understand. In terms of climate change, etc., then of course those interventional questions are the things that you want to change. Then again, you would go to these causal graphs, causal models. But in general, for different kinds of days, just for weather forecasting, there, just these correlations are really enough, right? Where you know that, hey, if cities are close by, they probably have similar weather, but if you have big mountains in between, then the weather can be quite different on one side or the other side of the mountain. So in that case, say San Francisco and San Jose, right? Knowing the weather in San Francisco will tell you quite a bit about the weather in San Jose. But here, since you have like mountains in between, then probably San Jose and Las Vegas will not tell you as much about the weather, say, if you already know Los Angeles. So there, really, an undirected graph is sufficient usually for different kinds of, for this particular application. Okay, so depending on the application, you'll want to use different kinds of graphical models, and we will be discussing all of these different kinds of graphical models. Okay, so where do these graphical models come from, and what are they? So I kind of already provided the motivation. So it's a way to represent joint distributions. Now, of course, you could say like, maybe I just don't even need it. I always assume no constraints on the joint distribution. And with that, you can represent any distribution, obviously. But, sometimes you may want to actually have some constraints, right? That helps you in terms of computation time. So you can actually do things in simpler distributions that you cannot do on, if you don't have any constraints on your distribution. It also helps you in terms of interpretability, right? If I go back to this example, right, in the end, this graph here, this causal graph, obviously this distribution that I can represent with a sparse causal graph can also be represented with a dense causal graph. But, in terms of interpretation, you're going to lose basically the interpretation or much of the interpretation that you would actually be able to get out of a sparse causal graph. So these are two motivations, right, to really have an economic representation of the joint distribution. So for computation's sake, but also for actually getting something that is more easily interpretable. In terms of origins of graphical models, they can really be tracked back to 3 different communities, and they'll actually come in quite important. And let me just say this, and then I see that there is in the chat something. So in terms of communities, where this all started off, we have statistical physics on one side, and that's really where undirected graphs have been important and have been used. The Gibbs distribution, Boltzmann distribution, same thing. And we'll talk a little bit about this. And then you have genetics, where, as clearly as I showed on the previous slide, it's directed. And in particular here, the motivation actually came from studying inheritance. And that was Sewell Wright. And then also statistics, and all of these things happened kind of at the same time. In statistics, actually, there were Bartlett, etc. They were describing interactions, in this case, in contingency tables. So these are just, tables of like how many people have black hair and brown eyes and height of, I don't know, above 170 centimeters or something like that, right? So these are contingency tables, like can be high dimensional contingency tables, where again, you want to understand something about the interactions between the different variables, say, the interactions between hair color and eye color. And also their graphs were used to represent these interactions. These were usually discrete models, right? These contingency tables are discrete. And again, here, usually they were using undirected graphs. And now let me go to the chat. Perfect. So there is a question. So are the graphs weighted by the extent of dependence or causal relationships? Perfect. So we'll definitely get to this. So yes, the graphs will be weighted. And the question is, what are these edge weights actually, and what do they represent? And we will get to this question as well. For now, it's just an edge will represent some kind of relationship, and we will have to define all of these things of what it actually describes. For now, the graph is just something that can actually describe, or should be something that can describe to you the whole distribution over the vertices. So, and in some sense from here, it already kind of becomes clear that there is like probability theory on one side and graph theory on the other side that somehow were merged together to actually build this very powerful framework for multivariate statistical modeling. And as you will see, and not so much in today's lecture, but more in tomorrow's and after tomorrow's lecture, is that, this framework really directly leads to algebraic, geometric, and combinatorial questions that come up when you actually study graphical models, when you want to use these graphical models. So that will be, more in the next 2 lectures. So today I just want to set up, really define what these are, and just set up everything so that we have a bit of also a framework to actually work in the next lectures. Okay, so this is the overview. So as I said, so today I'm just going to give an introduction to graphical models. So probably some of you are already familiar with it. I certainly saw faces who are very much familiar with this, who will actually probably be familiar with nearly everything I'm going to say. So that's today's lecture, is just really formally introducing these graphical models, setting up the framework. And then in tomorrow's lecture, I'll talk about the undirected setting. So, and I'll in particular look at Gaussian graphical models, so where the joint distribution is a Gaussian distribution, and tell you a little bit about the interesting algebraic structures and constraints that actually show up there. And I'll introduce a positivity constraint and show you how this is used. It's a particular positivity constraint on the distribution. It can really help you in terms of representing the distribution via graphs. Since this is all about geometric constraints in this school, I thought this might be a nice geometric constraint. And then in the third lecture, I'll talk about the directed setting. So where you actually want to, where the directed graph represents causal relationships. And again, I'll talk about the problem of learning the underlying graph. Right, there are somehow two parts. So one is either you just assume your graph is known, and then maybe you just want to learn the edge weights, which could be, how strong is a causal effect, as was asked in the chat. Or even the other question is maybe, well, comes usually before you go there, right, is actually to learn the graph itself. And so that's what we're going to do in this third lecture. And there you'll see that somehow combinatorial structure and geometric structure will actually play a very important role. Okay, so that's the overview. So second and third talk are more like real talks. So I'll actually have slides and everything. This talk is just to set up the whole framework. I thought it's much better so that I actually go slowly through it, through the math, that I actually write it out. And so that's what I'm going to do. So you might see my face is somehow going a little bit down because I'm going to put this over and I'm going to write on the screen. So hopefully it will all work nicely. Okay, but let me know if you don't, if you need to see me more or, yeah. Good. Okay, so let's get started about graphical models. And is there another question in the chat? No. Okay. Good. So graphical models. So first of all, one ingredient is a graph, right? So the graph, and let me change actually the color is also great. Okay. So, and we'll be looking at the directed and the undirected setting. Okay, so it can either be undirected, and so my graph will always be written as G, and it will consist of a set of vertices V and a set of edges E. Okay, and my vertices V, and this is just to make it consistent with the next two lectures, they will always go from 1 to P. Now, unfortunately, distributions are also called P. So today you'll have 2 P's. But hopefully after tomorrow, there will be no more distributions. So this should all be clear. And as I said, so this graph can be directed or undirected. I won't do mixed today and tomorrow and after tomorrow, but there is, of course, also graphs that have undirected and directed edges, etc. I won't look at that at all. So these E, so they're either undirected or they're directed. In the directed setting, the graph will actually always be a DAG, so a directed acyclic graph. Okay, and why is that? So as I told you, the directed setting was introduced by Sewell Wright, and he came from genetics. And so for him, the directed graph represented inheritance. So this is causal relationships. And so causality can never have directed cycles, right? Because causality or inheritance always goes forward in time. So you'll never have any directed cycles. So something like this is allowed, right? There is a cycle, but it's not a directed cycle. But something like this is not allowed. Okay, so in the directed setting, I'll always be assuming that it is a DAG. So we have one ingredient, which is the graph. And now to this graph, we're going to associate a distribution. Okay, so I'll be associating to every one of my nodes. So here I have 4 nodes in this particular example. To every node, I'm going to associate a random variable. Okay, so in this case, I'll associate random variables to each edge, to each node. So in this case, I'll have x, so in general, since I always have p nodes, I'll have x1 up to xp. Okay, this will be my vector x. And so this has a joint distribution. And this joint distributions I'll call P of X. Okay, now unfortunately I have two P's and they're different, but this is hopefully going to be clear in the context. Okay, so now what do I want to do? So now I have a distribution over nodes and I have a graph, and I somehow need to say how they're all connected to each other, right? What does the graph tell me about the distribution? And so that's kind of the picture that I want to do. So I have a graph, and then from the graph, so the graph, what it will define is it will define two different things. So first of all, it will define a certain form of the distribution. So it will define a certain factorization of the probability distribution. I'll tell you an example right afterwards. But the graph, of course, if you just know graphs as like a mathematical object, well, and from graph theory, you also know that graphs define some kind of separation statements, right? For example, in an undirected graph, I would say a set of nodes is separated from another set of nodes with respect to a third set of nodes. If you remove the third set of nodes, these two nodes have no connections between them, right? So meaning that every path between a node in set A to a node in set B has to pass through a node in the third set. Okay, so there are these standard separation statements in graph, and hopefully they also mean something about the distribution itself. So from a graph, you get separation statements, right? And from the factorization, well, the factorization will imply different kinds of independent statements, or conditional independent statements. And I'll always write CI for conditional independence. And hopefully, right, these separation statements, so if the graph and the distribution are really well married, then hopefully the separation statements that you get out just from graph theory, right, is actually exactly the kind of separation statements or conditional independence statements that you get out from the distribution itself. So hopefully these two things are actually the same, right? That's what a really nice theory would be, is that all these things are nicely married. And let me just, a little example. I mean, this is a very simple example, but will maybe tell you already something. So if I just have two nodes, say it's directed or undirected, it doesn't really matter. And so here I have this defines some joint distribution, x1, x2, right? And I have another graph on two nodes, which is the one without anything. So, what would be an intuitive way of saying like the distribution should factor? Well, here I have an edge, so it's okay to have a term that has a mixed x1 and x2. And probably, if you have this graph, you would probably define, if it was in some form intuitive, right? You would probably define the factorization of the distribution for this particular graph with no edges to be just p of x1 times p of x2, right? There shouldn't be any mixed terms just because there is no edge. Okay, we'll make all of this, it's just to say that, these things have been introduced in a very intuitive way. Everything will be very intuitive how these distributions and graphs according to a distribution have been defined. And so if this is the factorization, when I don't have an edge, just p of x1 times p of x2, well, this factorization actually implies a conditional independence relation, or in this case, just an independence relation. Namely, it implies that x1 is independent of x2. Right, and it's exactly the definition that x1 is independent of x2. So you see how, from a graph, I can describe, for example, what it actually means in terms of the factorization of the distribution. The factorization will imply certain conditional independence relations. The graph itself also implies separation statements. Right here, x1 and x2, or node 1 and node 2, they're separated from each other. So hopefully, and this is exactly what happens in this example, a separation statement is exactly the conditional independence relation, namely x1 independent of x2. Okay, and so this is kind of the picture. This is actually, if I can just kind of convince you of like that this all works out in the directed and undirected setting, tell you what the factorization is with respect to a graph in the undirected setting, what it is in the directed setting, tell you how to read off separation statements in a graph in the directed and undirected setting. and show that these are actually the same and that these really merge together in these conditional independence relations. So that's all I want to do today, to really just explain this picture here and make this a bit more mathematically clear rather than just this little example here, which is maybe a bit too trivial. So are there questions so far? Okay, nothing so far. So then I will move on. Please just interrupt me whenever there is something that is not clear. And I'm not sure, is it okay for me to give homework problems, or how does this work here?
Yes, please.
I see. Okay, perfect. Good. So I'll do that. Okay, so I'll be first talking about the directed setting. Okay, so directed setting, we said it's always a DAG, directed acyclic graph. So in terms of notation, I'll need some notation where I'll denote by pi I. That will be my parent set. Okay, so this is all nodes in the vertices such that j comma I is in the edge set. By edge set now it's directed, right? So j comma I is in the edge set means that j points to I. Okay, so this is the parent set. And I see there's a question. Oh, I did here. Yes, I will give homework problems along the way, but not yet. Okay, so now let me get to, so I need to define two things in a DAG. I need to define what is separation statements, and then I also need to define, oops, and now somehow it all went away. Well, that's interesting. Okay, that's fine, I guess. So you got it, the pi I is the parent set. So this is all j such that j points to I. And so now I need to define the factorization. So, and why am I starting with factorization? So I could also start with separation, but I think factorization is really something that has been very intuitively defined for DAGs. And, if I would ask you to write down a factorization, so, I give you a DAG and you should tell me, well, what is the distribution that factorizes according to this DAG? Well, probably this is what you would do. And I'm really sorry about the different P's here. So this is the number of nodes P and this is the distribution P. So you would probably do something like this, right? So if I have a DAG, say something like this, 1, 2, 3, then probably you would say like, hey, the distribution should be something that factors like, P of x1 has no parents, P of x2 has no parents, and then comes P of x3 given times P of x3 given x1 and x2. Right, I'm just, it's a DAG, so I just start off at the bottom and I define the distribution just going all the way up. And that's exactly how factorization is going to be defined for a DAG, okay? Just in this like most intuitive way, and we'll see what happens out of defining it in this way. Okay, so first of all, note that if you define it in this way, well, then this means that any distribution can be represented by a DAG, right? Because, for any distribution, I can always, if you give me any distribution up to xp, well, I can always write it as P of x1 times P of x2 given x1, no matter what distribution it is, right? Times P of x3 given x1 and x2, times, etc., P of xp given x1 up to xp minus 1. Right? I can always do this. Hence, any distribution, it will always factorize with respect to a graph with respect to the complete DAG. Right? This is now shown on 4 nodes. So that means that DAGs are universal, right? I can describe any distribution I like. However, let's look at something that is maybe more interesting, namely DAGs that are not complete graphs, and see how factorization actually implies conditional independence relations. So if I go back, oh, here was the thing. So if I go back here, I did a little example. So if I have a factorization, it will imply certain conditional independence relations. And I want to actually see this happening now and try to understand what are the conditional independence relations that are in fact implied by a DAG. Okay, so let's do a little very simple example. So say I just have 3 nodes, x1, x2, x3, and say, this is my graph, x1, x2, x3. So I have one missing edge. So you would probably already think that, probably I have some conditional independence relation here, right? This graph here should be something like node 1 is separated from node 3 given node 2, right? If I remove node 2, then x1 and x3 are separated. Well, and that's exactly what happens. So let me just write out by this definition of factorization. Let me write out the distribution. Okay, so I have x1, x2, x3. What is the distribution? Just by this formula here, right? So it is P of x1, has no parents, then comes x2 given x1, and then comes x3 given x2. Right? It's always the node given its parents. Well, but now we also know that I can always write it out, right? Any distribution I can just write out by this, the standard conditioning formula. So this is certainly equal to this times P of x3 given x1 and x2, right? Well, now if every one of these terms is equal, and now I don't know how much everyone is familiar with conditional independence relations, but otherwise this is a homework problem, that this is exactly the definition of conditional independence. So if you have the distribution of x3 given x2 is equal to the distribution of x3 given x1 and x2, that in fact implies that x1 is independent of x3 given x2. Okay, and so that's exactly what you would want, right, to read off from this particular graph here. But now I want to do a little bit of a more complicated and tell you that maybe, so directions matter somehow. This is how you would read it off in the undirected setting. But in the directed setting, somehow directions actually matter. And I want to give you another example. Let me now do the example like this. And maybe I first say that if the graph was like this, and you could go through this whole calculation yourself again, you would actually get exactly the same. Okay, so in this setting, I would get exactly the same. You can go through it yourself, and it doesn't really matter. And obviously, I can also have x3 pointing to x2 pointing to x1. It would always be the same. I would always get the same conditional independence relation out. But now let me go to this particular graph here. And from an undirected setting, they're all the same. But from a directed setting, they're really not. And I want to somehow convince you that actually we're going to get out very different conditional independence relations. In fact, we will get out that x1 is independent of x3. And we will get out that x1 is not independent of x3 given x2. And up here, we would have that x1 is not independent of x3 itself. Okay, so up in these two examples here that we had, it was really the case that x1 is independent of x3 when we condition on x2, so when you remove x2, but it's not the case, right, that x1 is just independent of x3 because, here, think of it in the causal way, right? I have these edges pointing down, so if you change x1, then obviously x3 will change. So if I know something about x1, then I will know something about x3. So you certainly don't have this conditional independence relation. But let's think about it now for a moment, just not from a graph theoretic perspective. We'll have to get graph theory in it, but just from a causal perspective. And let's look at this particular one here. So if you think about it causally, it makes sense, right? Let's take a little example, like say x1 is mom, x3 is dad, and they have a child, which is x2, right? That would be described by this particular DAG. And, let's do inheritance, since this was all developed in terms of thinking about inheritance. Say we're thinking about a particular disease, which is a genetic disease. Well, then x1 and x3, if they are not related to each other at all, right? Well, then it's independent whether x1, the mom has a disease or the dad has disease, right? So we would have that x1 is independent of x3. However, why is this one the case? Well, once I condition on the child, right? If I know that the child has the disease, well, then the child needs to have it from one of the parents. Well, but then, so certainly they are dependent, right? But then also once you know that the child has it from the mom, well, then the probability that, the dad also has disease will go down, right? Because it could already be described by actually the mom having the disease and not the dad also needing to have the disease. Maybe it's easier to think about it in the other way, right? If you know that the mom doesn't have the disease, well, then it's more probable that the dad has the disease, right? Because the child has to have it from somewhere. So that shows you that x1 and x3 are not independent once you know x2. right? And once you know x2, then suddenly these two nodes are actually becoming dependent. So it really matters a lot. The directions really matter a lot. And in fact, and you can maybe convince yourself that this is still the case. Even if I have x4 down here, I still have the same. I have that x1 is dependent of x4 given x3 given x4. Given x4. Okay, it also doesn't matter whether it's a grandchild, right? You're always going to introduce these dependencies between the parents. So it's quite interesting, right, in terms of that, that these directions actually matter, and we need to somehow figure out a way of understanding these independent statements that you can get out in this like very complicated way by actually going through the factorization. We need to somehow have a graph theoretical way of just being able to read them off, right? I would love to just be able to get this graph and be like, oh yeah, just graph theoretically, it will actually be the case that x1 is independent of x3 given x2, that I have this separation statement. Sorry, here, that x1 is independent of x3. And so that's what we would like to introduce under the question. Yes.
I can't see anything below the lines that you've just drawn underneath the graph.
This one?
Yes.
Is this the last?
That's
oh, you cannot see down here?
Right.
Oh, wow. Interesting. Okay. So thank you for letting me know. So then I'll put it up here.
Some of us can see it.
Oh.
Yeah, some of us can see it.
Okay.
So I'm not
maybe
sure. Who was that? Was that Will?
Yes, that's Will. I've got a big bar across the bottom of my Zoom screen.
Oh, so you can move the bar. You can actually move it around.
Yeah.
Can you?
Okay, so I put it
I'll
back
try to
here.
figure out how to do that.
Okay.
Just click on it and move it around. Okay, good. So then we're all good then. I'll continue like this. Okay, so I want to figure out a way of actually just reading off from the graph itself what these conditional independence relations are. And so let me go there. So, and let's maybe do this. Let me do a little bit more complicated example, then it will already become a bit more clear. So I have here another example. And let's do the same factorization again. Okay, so now we have this game. So x1 has no parents, so it's just p of x1. x2 has parent x1. x3 has the parent x2. x4 has two parents, x1 and x3. And x5 has one parent, x1. Okay. And again, you could write out the full factorization as as you can always do, x2 given x1, x3 given x1 and x2. You got it, right? x4 given x1, x2, x3, and x5 given everyone else, x1 up to x4. Okay, and now again, as before, these things here, just because they all have to be equal, they will all imply certain conditional independence relations. For example, if we have here, if you look at, let's do this one here, or actually let's do this one here. So here, for example, what we would get out is that x4 is independent of x2 given x1 and x3. And here, for example, you would get out that x3 is independent of x1 given x2. Okay, and this is something that if you're not familiar with conditional independences, you should just try to prove it. So now the question is like, if you would just do this for any graph, you see that, right? What is happening here is somehow like in the general way of writing it up, I always condition on everyone that came before me, right? But then in this way that is the factorization that you get out of the DAG, you're only conditioning on your parents. So the node, so just because I can read off these conditional independence relations, a node will always be independent of everyone I was able to get rid of, right? So here, for example, you got rid of x2. Here, for example, you got rid of x1. Well, what are these? What are these nodes? Well, they're all the non-descendants, right? They're all the ones that came before that are not my parents. So I always get that a node is independent of everyone that came before that are not my parents, given the parents. Right? That's what you just get out by actually writing it in this way. And that's known as the local Markov property in the directed setting. So the local Markov property, and I'll always be writing this as MP, just says, and this is, I mean, if you can go through the proof, right? But now just based on this example here, you just do it via induction, you get that a node is always independent of its non-descendants, given its parents. And I need to introduce this notation. So pi I already defined, right, as the parents. And let me define what these non-descendants are. So where j is in the non-descendants of I, if and only if there exists no directed path that goes from I to j. From I to j. Right, a non-descendant is someone that doesn't come below me. It's just like everything is like kind of descriptive, right? How these definitions are done. And that you really just get out of, like this example, right? You'll see that, you know, always when I condition on my parents, everyone else doesn't matter anymore in the factorization. So actually a node becomes independent of everyone else that I got rid of, given the parents. So this factorization implies something which we call the local Markov property. So always that a node is independent of all of its non-descendants, given the parents. Okay, and now, of course, the question is this it? Like, or are there more conditional independence relations that can be read off by the graph or that are given by the factorization? And unfortunately, this is not it. Okay, so in particular, so this is not yet all CI relations. In particular, it turns out that, you know, if I have an example like x pointing to y and then I have a node z out here, well, so in this case, you would get that y is independent of z given the parents, right, given x. So you would get that y is independent of z given x. But, you know, it should be intuitive and you can just argue for yourself, since y and z, there is no connection at all. It should also, and between x, there is also no connection. Oops, what am I doing? And between x, there is also no connection to z. It should also hold that y is just independent of z, right? So there are certainly more conditional independence relations that, you know, they don't even require conditioning on the parents. So there are some that are left out. And, you know, maybe I will not go completely through it, but there is something known as, and this will be the global Markov property.
Excuse me, this is Will again. Can you explain how this local Markov property gives us, for instance, the first
this one
condition that you had? No, I'm thinking about x4 independent of x2 given x1, x3 in the top graph. I'm not seeing that at all.
Okay.
There's
so
a path
x4
from x4
is here.
x4. Yeah.
Yeah, but let's just go like this. So, okay, so how you would prove it is two different things and how it relates to the local Markov property. So how you prove it is just from this equality here. Right. Since I know that P of x4 given x13 is equal to this, I get that x4 is independent of x2 given x1 and x3.
Okay. Does it follow from the local Markov property or not?
Exactly, it does, right? So it's also equal to the global Markov property. So this is I, right? Is number 4. Now, who are, or in this case, who are my parents? It's 1 and 3. So I need to condition on these guys. And then who are my non-descendants? Well, there is actually more, but both of them would be my non-descendants. So actually the conditional independence relation would be even bigger. So it's not just that x4 is independent of x2 given x1 and x3, but in fact, I can also have that x4. It's also true that x4 is independent of x5 given x1 and x3. Does this make sense?
Uh,
So x2 is a non-descendant, right? Because it doesn't come below x4.
I see. And X3 is a non-descendant as well?
Oh, okay. I know what you mean.
Ah,
The pi I is missing. So it's always independent of the non-descendants. By non-descendants, yeah, I usually mean without the parents, but let's take them out. So it's the non-descendants without the parents. Perfect.
okay, thank you.
Does it make more sense?
Yes, thanks.
Perfect. Okay, thank you for asking. That's perfect. Okay, so yeah, so they should be consistent, otherwise there is a problem. So okay, so this is how you would prove it, right? That from the factorization, you actually get out the local Markov property. So factorization implies the local Markov property. And then the question is, are there some more conditional independence relations that you don't get directly from the local Markov property? And in fact, there are. And for example, here we see that there are some more. Sometimes you don't need to condition on the parents. And so the global Markov property actually gives you all conditional independence relations that are possibly given by the Markov property. Is this xj or xi? Okay, I see. Okay, maybe a question has been answered, so that's good. Otherwise, ask, please. Okay, so let me say, what is the global Markov property? And it's again something in paths, but I think this will be a bit messy if I really do it. But so it has something to do with paths, and it is actually, and I'll just do it in words, and then maybe we can talk about it when I actually talk about directed graphical models in the third lecture. But it has something to do with, here actually, basically, I already gave you the whole intuition into it. And let me maybe just change the color since I'm going to draw on top. Okay, so here somehow I already gave you the whole intuition onto it. So you'll get out that two nodes are independent of each other given some set of nodes. And now this holds if and only if you have to look at all paths between these two nodes. Okay, so a node xi is independent of a node xj given some subset of nodes c. If I can look at any path between these two nodes, and somewhere along the path, I have one of these configurations. Okay, so what do we see here? So you see that, and I always look at triples of nodes. And so somewhere along the path, I would have to have one of these configurations. So either I have three nodes that come like this, the first node and the second node, and I have edges pointing this direction. And I am conditioning, you see here, I'm conditioning on the guy in between. Okay, so if I have the edges pointing through me and I condition on the node in between, then I'm breaking the path. Okay, so then I cannot pass through. And as you saw here, we got this conditional independence relation. And same is if you have a path, okay, I am looking at all these paths, and somewhere along it, I see this configuration here where I have two edges pointing out. And again, if you condition on the fellow in between, this path is blocked and I cannot pass through. Okay, and now comes the interesting one. So maybe you get to see this configuration somewhere where you have two nodes pointing into a third node. And now this path is blocked if you don't condition on the node in between. Right here, if I don't condition on the node in between, I actually get an independent statement. If you do condition on it, I can pass through. I can walk through. Okay, and so in fact, just look at every path between any two nodes and just applying these three rules here that you have here, right? So you look at all triples along the path and you just look at, hey, is this path blocked somewhere? If every path is blocked, then that means that these two nodes are conditionally independent given the third set. Okay, so I know that this somehow doesn't make so much sense in terms of going, because this requires like a couple of hours to really understand it. But I think what is really important to know is that there is this really nice kind of graphical criterion, which doesn't just use the undirected graph, but actually use the directions, as you see here, right? Because, you know, the directions matter, right? When you have two nodes pointing in, well, then it's very different than having all other kinds of combinations of nodes pointing out or nodes or edges pointing through the node in the middle. Okay, and so there is this graphical criterion, and it's in fact really like how I described it now. So there's even an algorithm to efficiently check whether every one of the paths is closed. It's known as the Bayes-Bol algorithm. So it's the Bayes-Bol algorithm. I have the reference at the end. So this one will actually check all these paths and just figure out whether every path between any two nodes is blocked. And if it's blocked, well, then you have a conditional independence relation. And why it's Bayes-Bol? Well, you can think of it as a ball rolling around, you know, on every one of these paths and just checking whether somewhere along the path someone says, hey, you're blocked, right? And the blocking just comes from these rolls here. So I think it's anyways, you know, it's too much to just understand or be able to grasp, at least for me, in an hour. But I think what is important to know is, hey, it is not all independent statements, but there is a way just from the graph of actually reading off all conditional independence relations that hold. Okay, and if you want to know more, this is what it is called. It's the directed global Markov property. There is an algorithm for actually reading them all off. It's this Bayes-Bol algorithm. And I do have the references on the last slide. Okay, and so now I just get somehow to the main theorems. And so what are these main theorems? They just say what we had on the first picture, to actually say that everything is nice and consistent and, you know, it's all good. Okay, that namely, that if you have factorization with respect to a DAG, then that's equivalent to the directed local Markov property. And in fact, this is also equivalent to the global Markov property. Okay, so that really means that, you know, from, oops, I don't know why it's not moving forward. Okay, so let me just leave it. So from the local Markov property, in fact, it already implies all of the conditional independence relations. It's just that you cannot really just read them off from the graph, right? So there will be some that are missing, but they will be implied as a distribution statement. And all of this is equivalent, okay? If you can factorize, if the distribution factorizes, then in fact, you get all of these conditional independence relations that are described by the local Markov property, and it goes the other way around as well. Local Markov property, in fact, implies that you will factorize with respect to that DAG. So everything is nice and consistent. And in fact, it is the case that the global Markov property is complete, meaning you cannot add in more conditional independence relations than these. So if I denote by I of G, so this is all of the CI relations given by the global Markov property. Okay, global Markov property. And you have I of P is the CI relations in P, in the distribution P. Then in fact, it turns out that, you know, for any DAG G, there exists a distribution P of X such that, you know, these two are in fact the same. Distribution that factorizes according to G, that factorizes with respect to G, and there exists a distribution that factorizes with respect to G such that I of G is equal to I of P. Okay, so there will be one that really has exactly the conditional independence relations that you want. And hence, you know, from factorization, this is all you can get. Okay, I cannot get more because then there will be a distribution that doesn't satisfy more. So there is for sure a distribution that satisfies exactly these ones that you get from the global Markov property. And so that's complete. Okay, So there is no more. There can be distributions that satisfy more, but in general, they don't satisfy more. So if you factorize, then in general, the only conditional independence relations that you satisfy are the ones given by the Markov property. And so now in terms of homework problems, I think what would be good to do is to actually try to find, so there exist distributions. So here I'm just saying for any DAG, there exists a distribution that factorizes, and so that these things are equal. But there also exist distributions for that which there is no DAG that is actually exactly describing the conditional independence relations. So there exist distributions for which there exists no DAG G with I of G is equal to I of P. Okay, so there are certainly distributions that cannot be represented by a DAG, so that the conditional independence relations are exactly the separation statements. And it would also be nice to show that you can in fact have different DAGs. So there exist DAGs G1, G2, G1 not equal to G2, such that I of G1 is equal to I of G2. So these separation statements in a DAG actually do not uniquely identify the DAG. And we will talk a lot more about this, not tomorrow, but the lecture afterwards, because this is really important, right? So if somehow these conditional independence relations do not uniquely identify the DAG, well, then if we're thinking about learning a DAG, well, that means that you can only learn something like an equivalence class of DAGs, right? I cannot learn more because all I can get out of a distribution are the conditional independence relations. But the conditional independence relations, they only identify a DAG up to some equivalence class. So there are some DAGs that just have exactly the same conditional independence relations, and so I will not be able to tell them apart. So this will become really important, and we'll talk much more about this one here. I mean, you can already look at it in terms of a homework problem, but we'll definitely, define and actually solve this problem also as a homework problem. In fact, next time, and not next time, the time afterwards when we're really talking about directed graphs. Okay, so this is a little bit of an overview on directed graphs and just setting up the whole problem. And so now are there questions? And otherwise, I'll also have to define the same thing for undirected graphs. It's a bit, now that I've done everything for directed graphs, it will be much easier. But I want to do exactly the same picture. And I really don't know why it's not moving forward. I want to do exactly the same picture also for undirected graphs on the next slide. Any questions so far in the directed setting? So what we just did is in the directed setting, just shown this little picture here, right? This picture here. We showed what does it mean to what does factorization mean with respect to a DAG, and what does separation mean, and that the two things are actually the same. I mean, factorization implies some conditional independence relations. The graph also implies some separation statements, and these are exactly, you can actually read them off from the graph. They're exactly the conditional independence relations. So there is this very nice marriage between graph theory and probability theory that was defined in the directed setting. Another question. Not blocking x1 and x3. Okay, so there is some question and we need to figure out where. Could you unmute yourself and ask it? Is it here? Probably.
Yeah, there. The last line.
Yeah, so, okay, so let me change the color so that I can do it in red again. So this line here, so here I have a dependent statement. So it doesn't block. So x4. So if you condition on x4, then you can actually walk through. And so the question is, why is this the case? Is that the question?
Yeah.
Okay. So graph theoretically, how you could see it is, and let me maybe go to the next slide where I have a bit more space. So if I have So I'm just going to explain why is it kind of the same thing as this. So I have this. If I condition on x2, you can walk through, right? This was clear from this particular example. I hope this one is clear. So then now I'm just explaining why is this the same case using the baseball algorithm. If I unravel the path that the ball is going to take, the path looks like this: x2, then the ball goes down to x4, then the ball comes back up to x2, and then it goes to x3. And so now if I condition, you see now I'm looking at this triple here, and I'm in this case. So when you condition on x4, I can walk through. When I don't condition on x4, I'm blocked. So whether you condition on something downstairs or already at the first level, it actually doesn't matter. Or I can even condition on something even further down. It really doesn't matter at all. You just have to unravel the path that the ball is going to take. If you want to think about it graph theoretically. If you just want to think about it probabilistically, it's maybe easier because this example of inheritance is quite clear, right? So if I know that the child has the disease, then that will introduce dependent structure between the parents. But in fact, it's exactly the same reasoning. If I know that the grandchild has the disease, well, then, you know, somewhere it certainly it introduces dependent structure between the grandparents, right? Because the disease has to come from somewhere. So it's exactly the same reasoning there as well. So you can argue through it in terms of graph theory or in terms of the distribution. Does this make sense?
Yeah, thank you very much.
Okay. Perfect. So I guess I have, what, 5 minutes? 4 minutes. Okay, so maybe I should do the undirected setting also next time. But I think I can just do it maybe in words a little bit. So if I have the undirected setting. So in the undirected setting, somehow if you come from a graph theory, now here it's very easy. So before it was easier to just write down what I think the factorization should be. In the undirected setting, actually factorization is kind of hard because, and you know, you can kind of, well, you know, the maybe most intuitive way to write down a factorization would be maybe something like, you know, maybe something like this. Maybe it is something like, I don't know, xi and its neighbors. Yeah, we don't have parents, right? So maybe it's its neighbors. But you can convince yourself that nothing like this will actually be consistent. I mean, I can define, you know, I will define this part here. Oops. Well, I'll define it for each node, but then at the end, you need to get back the full distribution, and you can actually show that, you know, none of these definitions will actually work out. So this will not give you something that is consistent. So actually just writing out the factorization, just coming up with a way of factorizing the distribution according to an undirected graph is actually difficult. But what is easy from a graph theoretical perspective, I guess, you know, there is already a standard way of saying that two nodes are separated, right? So in this case, you will be like, hey, you know, x2 is separated from x4 given x1 and x3, right? Because if I remove x1 and x3, then there is no path between x2 and x4. So there is a very intuitive way of saying that, you know, what the global Markov property should be. Right? So the global Markov property should be this. It should be that, you know, XA is independent of XB given XC. For all, you know, whatever, even subsets or separate nodes, whatever you want to do. If, you know, A comma B are separated in the graph when removing C, right? So, and this is exactly how we're going to define the global Markov property in the undirected setting. So just coming from graph theory, this is how you would define separation statement, right? And these are hence the conditional independence relations that we want to use. And now what I have to do is somehow define what is the factorization, which will exactly give me these conditional independence relations. And so what has been done, and I won't write it out here, but just so that you know it, is, in fact, as I said, it comes from statistical physics, right? Physicists have thought about undirected graphs for a long time. And in fact, the Gibbs distribution, which is the same as the Boltzmann distribution, is a distribution on an undirected graph. And interestingly, that distribution exactly leads to these conditional independence relations. So the way we defined it is exactly the one that will nicely give you exactly the conditional independence relations that you would get if you just, define separation statements on undirected graphs. And so I'll write that out next time. But if you know the Boltzmann or Gibbs distribution, then that is the right way of factorizing according to an undirected graph. You want these two things to be nicely connected, so that somehow this picture that I have here on the slide, so that this picture here, in fact, will work out. Okay, and I'll finish this up next time. But this is just a little bit of the introduction of showing you this nice marriage between somehow graph theory and probability theory to define something that is known as a graphical model. Now you can maybe see my face completely. So are there questions? And otherwise, I'll just continue next time. I'll actually write it out for the undirected setting as well. And a chat question. Will you be talking about semi-graphoids tomorrow? No, I will not be talking about semi-graphoids tomorrow. So if anyone cares about semi-graphoids, so these are all conditional independence relations that are implied by each other. So I will not be using this, but it is a very interesting topic. And I suggest that you look at it if this is something that you care about how do different conditional independence relations imply each other. So tomorrow I will be talking about a little bit on undirected Gaussian graphical models and different kinds of geometric constraints that come out of this. Any other questions?
You had a main theorem, a kind of structure theorem about the local Markov property and the global Markov property, saying that the global Markov property was complete. Can you just say a little bit more about that? I'm finding it very confusing to think about what this really means. What does it mean for the local Markov property to imply global relations?
Yeah, so the local Markov property is just a set of conditional independence relations. And it's actually very much related to Mira's question. So the local Markov property, how I defined it, is a set of conditional independence relations. The global Markov property is also a set of conditional independence relations that you can just read off from the graph. Okay. Now the local Markov property, so the conditional independence relations in the local Markov property are always contained in the conditional independence relations in the global Markov property. In general, they're not the same. Okay. However, now, what does it mean that one in fact implies the other, which is the theorem, which is here, this equivalence, okay? So it means that, there are additional constraints, right? It's not just a graph. We know that this is a distribution. So it has to be a distribution, meaning, if you take the integral, it would integrate to 1. So by us knowing that it has to be a distribution, actually these setup you can show, and this is, for example, through semi-graphoid properties, you can show that these conditional independence relations, they will imply more conditional independence relations just because it has to be a distribution. And in fact, you can show that this small set of conditional independence relations will imply all the big set of them just because it has to be a distribution. Does that make sense? So that's why I have here an equivalence. That makes a lot of
sense. Yes, thank you.
Yeah. So those are great questions, but just as sets, right, they're not the same. But because I know more that it is, those are conditional independence relations in a distribution, then they actually imply each other. Great questions. And so these would, and maybe since I have the references, all proofs of everything I said today is in this book. These are the three foundational kind of, I told you based on the history, right, that it comes from 3 different areas. So these are the foundational kinds of papers where it comes from. Besagnot, Bartlett. I have it here, right? Sorry, my order is. So these are the 3 foundational papers from the first slide. And then, Okay, so these I will talk about. This one here is a paper about the baseball algorithm, if you want to see how to actually read off all conditional independence relations. And Perl, etc., and Verma and Perl, these here are all of the papers where you can actually read off, what is this global, everything is in here. So I would just go to this, but these are the original papers of, what are all these conditional independence relations that are implied by a directed acyclic. But if you want to read off a bit more, this is the standard textbook, super nicely written by Stefan Lauritsen on graphical models. There is one chapter on Markov properties.